Lightning flickers somewhere in Earth's atmosphere dozens of times every second. Most of these electrical flashes remain in the clouds, with only about a fifth of them reaching low enough to strike trees, buildings, or the ground. Yet lightning bolts in the clouds deliver a unique and powerful punch of their own. They're directly linked to events that produce some of the highest energy radiation naturally found on Earth: terrestrial gamma ray flashes, or TGFs for short. Thanks to recent work by NASA's Fermi Gamma Ray Space Telescope, scientists have come a few steps closer to understanding these extraordinary outbursts. When lightning flashes high in the clouds, its energy may alter the strong electric fields near the top of the storm. About 1,000 times each day, this sudden change triggers an upward surge of high-speed electrons. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when they're deflected by air molecules. TGFs happen quickly and randomly, so even catching them by satellite has been difficult. But new results from the Gamma Ray Burst Monitor on Fermi are giving scientists fresh insights. Last year, the GBM team showed that TGFs located well away from Fermi produced beams of charged particles that could travel along Earth's magnetic field and hit the satellite. Now, thanks to advancements in data processing, Fermi's GBM is better at detecting TGFs than ever before. As a result, scientists have discovered that radio signals, once thought to be produced by the lightning that triggers a TGF, are in fact broadcast by TGFs themselves. Each lightning stroke creates a burst of very low-frequency radio waves. Through the Worldwide Lightning Location Network, scientists use this unique radio signal to track electrical activity around the globe. For some time, scientists have known that TGFs were associated with strong radio signals, so it was natural to think that these radio signals were produced by the lightning stroke that triggered the TGFs. Here's one instance that highlights why the GBM team now questions this interpretation. It's August 2009, and Fermi is flying over thunderstorms off Mexico's west coast. Each symbol marks the location of a lightning bolt detected by radio waves. The highlighted circle shows how much of Earth's surface Fermi can see at any given moment. Just as the satellite passes over the storms, a TGF occurs. There's no other lightning near that position when Fermi detected the TGF. After studying hundreds of TGFs and comparing them to radio-based lightning locations, the GBM team concludes that both the gamma ray and the strong radio emission comes from the TGF. The team also finds that weaker radio bursts, occurring up to several thousandths of a second before or after a TGF, actually represent the individual lightning stroke associated with it. The GBM findings confirm a theory published in 2011 that the same avalanche of speedy electrons that creates a TGF's gamma rays also produce strong, very low-frequency radio signals. With this knowledge, scientists can pair the Fermi TGF sample with the more precise radio positions from the Worldwide Lightning Location Network. This will clarify weather patterns associated with TGFs and usher in new studies, perhaps helping scientists determine which types of thunderstorms produce some of Earth's highest energy natural light.